Okay, so today we will begin discussing the postulates of quantum mechanics. And let me begin by asking this question to all of you. What do you think is quantum mechanics? I mean, when you hear the word or somebody asks you, what would you say? So let's ask Munib.
Quantum mechanics is basically particles and study small scale physics.
Okay, so study of particles at small scale. Superposition, entanglement. Okay.
और कोई भी हमारे पास इलेक्ट्रॉन के लिए हम एक वेव फंक्शन है जो डिफाइन करते हैं.
Okay, good. Thank you. So, Osama, what do you think? What quantum mechanics is?
Study of particle at quantum level. Then small tablet can be very cool and you can.
So, study of particles at quantum level. What do you mean by quantum level?
Quantum वो levels पे quantum behavior particle का dominate हो. यानी उसका wave function या उसकी superpositionness में जाहिर हो. बटा तो ये कंप्लीट क्वांटम बिहेवियर है, लेकिन इसका क्वांटम बिहेवियर से हम ये क्वांटम बिहेवियर इसका भी शो नहीं होगा. एक जब ये बहुत छोटा हो तो हमें इसका क्वांटम बिहेवियर शो होना है.
चलिए, good. So, Subhan, what is quantum mechanics? I mean, we are discussing कि अगर आपसे कोई पूछे कि quantum mechanics क्या है, so what will you answer? So it's a mathematics that describes the behavior of the particle. Good. और कुछ इसमें ऐड करना चाहेंगे? Okay. Okay, good. Thank you. So, एक सवाल ये भी आता है कि क्लासिकल मैकेनिक्स भी तो मैथमेटिक्स ही है ना, मैथमेटिकली डिस्क्राइब करते हैं. सो व्हाट्स द की फीचर that separates it from classical physics? जी, ओके, probabilistic. जी, आपका क्या नाम है? जैन. जी जैन.
क्लासिकल मैकेनिक्स है, वो आपको बॉडीज के मूव कैसे करेंगे विदाउट डायनामिक्स, इनके मैकेनिक्स के बारे में हमें पता लगता है. आपके लॉज ऑफ मैकेनिक्स हैं जो सारे मोमेंटम के, जिस तरह से भी सब चीजें आपकी. तो एक लेवल आता है, एक पॉइंट आता है कि जब वो क्लासिकल मैकेनिक्स आपका चीजें एक्सप्लेन नहीं कर पाता, जो मैकेनिक्स हैं वो जो मूवमेंट या मोशन की चीजें हैं वो पार्टिकल्स पे वर्क नहीं करती एक स्मॉलर स्केल के ऊपर. तब जाके फिर आप अपने मैकेनिक्स को डिफरेंटली एक्सप्लेन करते हैं मैथमेटिक्स के थ्रू. वो क्वांटम मैकेनिक्स.
Okay, good. So when classical mechanics, stops explaining things, then we go to quantum. That's first thing. Okay, so Heather. Okay, so basically you are saying that quantum mechanics means it's probabilistic. Okay, good. Thank you. So Abdullah.
That could be
Okay. सबीता, आपका नाम सबीता जी? सबीता, आपका क्या ख्याल है? हाँ हाँ, व्हाट इज क्वांटम मैकेनिक्स?
is basically the study of particles in the molecule. Then we realize कि हमारी जो observable
Okay, thank you. First of all, I'm really glad that I asked this question. So, because it shows me two things. Number one, कि most of you know something. लेकिन मेरे ध्यान में वही पिक्चर आ रही है हाथी की, कि कुछ काम में से कान को डिस्क्राइब कर रहा है, कोई टांग को, कोई उसकी टस को, कोई किसी चीज को. सो जी आप.
थोड़ा सा डिफरेंट है पॉइंट.
हाँ हाँ, श्योर श्योर.
सर मतलब मैंने जितना क्वांटम मैकेनिक्स को पढ़ा है सर, आई बिलीव कि क्लासिकल मैकेनिक्स से इसका पूरा लॉजिक ही डिफरेंट है. मतलब क्लासिकल मैकेनिक्स में व्हाट डू यू डू, वी यूज द सेट थ्योरी लॉजिक, लेकिन इसमें वेक्टर स्पेसेस का लॉजिक. और इनकी जो मैथमेटिक्स है वो फिर इसी तरह डिफरेंट वर्कआउट करती है. वहाँ स्टेट्स अगर आप पॉइंट से रिप्रेजेंट कर रहे हैं तो यहाँ आप वेक्टर से रिप्रेजेंट कर रहे हैं. और वहाँ अगर स्टेट का जो लेबल है वही मेजरमेंट को डिफाइन करा, तो यहाँ जो स्टेट है वो बेसिकली आप मेजर नहीं कर रहे हो. सो दैट्स अ डिफरेंट थिंग दैट कम्स आउट ऑफ मेजरमेंट.
गुड, यू आर गेटिंग बिट क्लोजर. ठीक है. सो आपका जो रिस्पॉन्स है, आई थिंक मच क्लोजर टू व्हाट आई एम गोइंग टू से. तो क्वांटम मैकेनिक्स जो है, वो आप सब लोगों ने जो चीजें डिस्क्राइब की हैं, वो ठीक है कि दे आर पार्ट ऑफ आवर नॉलेज थैंक्स टू क्वांटम मैकेनिक्स नाउ. बट क्वांटम मैकेनिक्स इजंट दैट. जैसे ये नहीं है कि वो क्लासिकल को एक्सप्लेन नहीं करता, या बड़ी चीजों को एक्सप्लेन नहीं करता और छोटे पार्टिकल को करती है, या वहां पे एप्लीकेबल है, यहाँ पे नहीं है, यहाँ पे प्रोबेबिलिस्टिक है. सो क्वांटम मैकेनिक्स is actually a framework to think, to describe theories that people developed in the a few decades of last century after several experimental results that came into light, and people were not able to understand the outcomes of experiments based on the classical thinking. So just to give you an idea what quantum mechanics really is, let me actually start from classical physics, just 5 to 10 minutes, and so that we can compare what we really mean by quantum mechanics and what's the difference. So, जो classical physics है, let me start with that. आप बल्कि इसको क्लासिकल फिजिक्स में कहें, क्लासिकल फिलॉसफी जो है. So classical philosophy was developed by observations of humanity with their eyes and ears, and by looking around, and these were the sort of postulates that were developed. So let me try to make up these axioms. You probably wouldn't find them written anywhere, so this is sort of my way of then trying to make a jump from classical to quantum, and so that you are able to place quantum mechanics at its rightful place. So let's say, what's the first axiom of quantum classical philosophy? So the classical approach hai, its first axiom is this, that you can describe the state of a particle, and it doesn't matter कि particle छोटा है या बड़ा है. Okay, so it's a secondary thing, it has nothing to do with it. By, let's say, its position and its velocity. That's the first and sort of fundamental assumption of classical physics. It doesn't tell you कि particle की position क्या है या velocity क्या है given situation में. That's a derivative or a secondary thing that you can do in a particular situation. But it would say that whatever theory you are going to develop, for example, classically problems क्या थे लोगों के सामने, trying to explain the motion of stars and planets and moon. So these sort of objects are maybe the trajectories of cannonballs of coming out of cannon and so these other these types of things. So this was the fundamental assumption. Okay, and it was very natural to assume, you can say, because if you think classically, you fire a cannonball, let's say from here, and you look at it, and you are continuously looking at it, and it's going like this. So people knew that, okay, practically it might not be possible for us, to exactly say what is the position and velocity of the cannonball at right this instant of time. But they said that's only a matter of practicality. In principle, you can do that. You can perhaps put somebody over there which can continuously record position, time, velocities, etc. And you can know these things. So it's only a matter of practicality and not the matter of principle that you can find the position and velocities of these particles at each instant of time. So this was the first fundamental assumption. So if you go beyond Galileo, they didn't even know what are the kinetic relationships between these velocities and positions at this point in time and at a later instant. These were the empirical laws discovered by Galileo later on, but they were discovered based on this assumption that you can describe the trajectories and the behavior and dynamics of particles by something like this. And then they were, we can say, the second axiom, which was debated back and forth many times about the force. Okay, if you apply force, can you have to be in contact, or can you apply force from a distance, or whatever? But in times of Newton, it was discovered, okay, the force and the force causes changes in motion, and those Newton's laws. So that was the second thing about the dynamics. And then there was another, fundamental assumption, which is, again, I'm saying that these classical philosophies, axioms, you might not see anywhere. That's my way of connecting with what is going to come in quantum physics. And then, so for dynamics, the fundamental assumption was this, that there are some relations which connect, you can say x1, v1 at t1 at with some later, time. It doesn't. So those relationships are not fixed. So, for example, the equations of motions discovered by Galileo and Newton were later turned out to be not always applicable at high speeds. So special theory of relativity modified those relations a little bit. But still, even in the special relativity theory, these assumptions were still there. That you are talking in terms of position and velocities and accelerations and these types of things. Okay, the third thing is about measurements. So there was this fundamental assumption that you can measure, since you're talking about position and speeds, there has to be an implicit assumption that you can always measure the position and speed and acceleration and time of these particles at at any instant or at any position during their behavior. It doesn't matter if you are not able to measure these things with high precision, that's okay. But there was no barrier of principality. There was no in principle barrier that you can't measure it. Okay, you only have to invent a better clock, for example, to measure time. Instead of using your pulse like Galileo, you might have to come with these clock, and then later with this all those clockworks of gears that you invent better and better way. But there was no fundamental limit from the classical philosophy on how precise you can go. So these sort of you can say three laws that govern them, and we can actually also perhaps state a similar assumption about observables, that the observable or physical quantities associated with something are quantities that you can devise some apparatus to measure directly, at least in principle, without disturbing the particle. Okay, so these were the settings. So in the classical philosophy, okay, sir, you might have to, invent better and better measurement scheme, or it didn't tell anything, okay, if you want to measure velocity, what sort of instrument you should use or what scheme you should use. That's a secondary thing. And that's something for people who are trying to, work out these things, they are working at. Similarly, for observable, you can, come up with any physical quantity that has to be a real number, because a real number would make sense of what you're talking about, for example, energy or position or its momentum and these things. So this was a framework. This was the classical philosophy. And no equations are fixed. The equations continue to change from, you can say, uh, in time, prehistoric time, and then solidified by Galileo and Newton, and then modified a little bit by Einstein as well when something more were discovered. But until special relativity theory, all of these things were sort of the cornerstone of classical physics. It didn't tell you, okay, how are you going to construct a theory of electromagnetics? But even in constructing theory of, forces of that charges or magnets impinge upon one another, these things were still fundamentally operating at the bottom. Similarly, while Newton was trying to discover a theory of gravitation, he was still operating upon these fundamental assumptions. Its gravitational law is essentially in this framework. So this is, you can say, classical mechanics. Now, when we go to quantum mechanics or quantum physics, so first of all, you shouldn't have this thing in your mind, this dichotomy, okay, quantum physics is applicable for small particle and not. It's totally nonsense. Quantum physics, as we know, it's applicable to everything. And it's not a theory that will tell you, okay, how the particle move from here to here, or what should be the forces between particles in a nucleus and so on. It's those are the secondary things. It gives you a framework to come up with those theories. And corresponding to all of these, there are sort of axioms or postulates that the quantum physics rests on. And I'm sure that you might have encountered them in a few courses. And what we are going to do today and in the next week, I'm going to review those postulates and provide the mathematical foundations for each one of them, so that after 2 weeks, when we start working with the quantum systems, we have a framework to sort of work out the theories. And now let me sort of write the theorem, the postulates quickly over here for quantum physics, and then I will start with one postulate in each lecture. So in quantum physics, these sort of governing postulates are dramatically different from these postulates. The first postulate is that the state of a system is not given by its position and velocity, but it's given by a ray. State is given by a ray in Hilbert space. This lecture actually is devoted to this first postulate. So I'll explain this thing in detail, especially what we mean by Hilbert space and what do we mean. Ray is just a normalized vector. So now the first fundamental difference in our understanding is this, that the state of a system, state of a particle is given by a ray in a Hilbert space. And it is true for everything. It's true for this chart. It's true for me as a, collection of particles. It's true for electron. It's true for proton and everything that you can think of. No distinction. Okay, the quantum physics will start when classical physics stops, giving you something sensible. Then you go to quantum physics. This is the operating principle. This is the axiom, and the axiom that I'm going to list later on, and this one, they were not discovered overnight by someone. Okay, somebody woke up one day, okay, and just started writing, let's start using these axioms from now. They were forced onto people in about 3 decades from 1900 to 1930s. That when people were trying to explain those experiments, they eventually led to these axioms, that the operating axioms and operating philosophy, it's better actually to call it philosophy. The operating philosophy of trying to make sense of those experiments was actually wrong. So that's why they had to invent a new philosophy, a new way of thinking, or you can call it a new framework. या जैसे आप में से कुछ लोग mathematics भी कह रहे हैं, it's a new mathematics. It's a new way to specify the state of the system. So this is the first axiom of quantum physics, that the state is given by a ray in a vector space, in a special vector space. So that vector space is a Hilbert space. We'll spend this lecture on Hilbert spaces. The second axiom corresponding to, let's say, these observables is that the observables are given by self-adjoint, or let's use Hermitian for now, Hermitian operators that operates, on this ray and give you some information about that thing, the physical information. Remember, quantum physics doesn't tell you कि हिल्बर्ट स्पेस किसी पर्टिकुलर सिस्टम के लिए क्या होगी, चाक के लिए हिल्बर्ट स्पेस कैसी होनी चाहिए, इलेक्ट्रॉन के लिए कैसी होनी चाहिए, किसी और सिस्टम के लिए हिल्बर्ट स्पेस कैसी होनी चाहिए. Doesn't, and that's not the job of quantum mechanics, so to say, because this is just a framework to which gives you, a way to postulate different, let's say Hilbert spaces or different ways of representing a system. That's where, so this is a way to discover theories. It's not in a sense a theory itself of anything like a theory of gravitation or theory of, let's say, electromagnetics and so on. It's not like this. It's a framework in which you can use to discover or write theories that describe physics of a particular, system. So this is the first axiom, that you represent states by a ray in a Hilbert space. The second is the observables have to be Hermitian operators. And then about dynamics, that the state evolves under, unitary operation for closed quantum systems. And using this axiom of, evolution, we will be able to understand the evolution of an open quantum system, because open quantum system is essentially like two quantum systems interacting with each other. So this axiom tells you that the evolution has to be unitary for the whole quantum system. And using these tools, we will be able to understand how the evolution of parts of system can be understood and how we can, think about them. So first of all, you see this evolution mechanism is somewhat different, but perhaps not too different if you compare with classical physics. The major difference actually comes with these 2 points. And the fourth one that I'm going to write, which is about the measurements. So measurements are given by Hermitian projective operators. We will discuss these things in detail. And that's where the probabilistic nature of universe around us comes. And from this point onward, never say, okay, quantum mechanics and classical mechanics, the difference is quantum mechanics, you have those situations where you have probabilistic outcome. It's applicable everywhere. Motion of moons, planets, everything in principle, okay? The matter of practicality is something else. But in principle, you can write a ray for the whole universe, perhaps, if you have, a big enough paper to write it on. And similarly, you can describe its evolution if you know all the potentials that it is subjected to. And if you want to find some observables, you can prepare these measurement operators. And then there is a fifth postulate, sometime, written separately, which tells us how to combine individual quantum system into a single quantum system. But none of these axioms tell us that what is the theory of electromagnetics now, or how the if I hit this particle over here, how this is going to move, what's going to be its trajectory. So this gives us a framework that I can now write theories that say of chromodynamics, how to describe particles in nucleus, or I can write theory of photons, how the electromagnetic field propagates, and so on. So when you are asked what is quantum mechanics, so the long answer is always this, but the short answer is perhaps that it's a framework which gives you a way to describe theories that you can postulate to sort of understand or model the behavior of different systems. And all systems are quantum systems. You don't have to say, okay, this is a quantum system. Just any physical system is a quantum system. There's no need of qualifying. Okay, so these are the postulates that I'm going to spend this lecture and the next 2-3 lectures trying to build more understanding and mathematical framework. And I'm going to do it in the setting of a closed quantum system. And then once we develop the tools for the closed quantum system, then we'll spend almost whole of the rest of this course on learning ways of describing open quantum system. Okay, so in actually a way you can think of this course as just a course in advanced quantum physics with a particular application in mind, which is relating to like quantum communication or quantum information systems. Because the theories that we will develop here are going to be applicable to condensed matter physics or many body physics, atomic physics, or anything you can think of, wherever we have many particles. Okay, so let me start with this first postulate now. अच्छा, मैं चाहता हूँ कि ये जो क्लास है थोड़ी जरा इंटरेक्टिव रहे, क्योंकि जब तक आप बोलते नहीं है तब तक पता नहीं चलता कि आपको पता कितना चल रहा है और मसाइल क्या है. ठीक है, so feel free to interrupt me anytime, okay? And I don't usually have any agenda every day. ये just मैंने अपनी सहूलत के लिए लिखा है कैसे मैंने फ्लो करना है, but we can be slow or fast. और वैसे भी चूंकि हमने ट्यूटोरियल सेशन भी हम ऑलमोस्ट क्लास के साथ ही चलाएंगे, तो we have plenty of time. So any question जो भी आपके ज़हन में आता है, you're free to ask. All right, so let me begin with the first postulate, which says that we can describe the state of a system by a ray in a Hilbert space. So आज का जो lecture I'm going to spend on sort of reviewing the linear algebra of vector spaces and Hilbert space. मेरी जो understanding है कि आप में से ज़्यादातर लोगों ने, बल्कि सब लोगों ने ये एक या दूसरी फॉर्म में देखा हुआ है. So I'll be little bit fast, but please feel free to interrupt me anywhere you want. So let's start from defining what a vector space is. Okay, so a vector space is just a set. If you think this thing in your mind, then the fear of word vector space goes away, because initially it seems to be a fearsome thing. Just that the elements of set have certain properties and very simple ones. So it's a set. Let me call this set some V, and we will represent its elements with Dirac's notation. Let's say this is the first element, this is the second element, and so on. So it has some elements. It could be finite, it could be infinite, and these elements are called vectors if this is a vector space. So this is a set that has certain elements, and it's called a vector space if it satisfies these properties. So number one is that it is closed under addition. It means that there is, if you add any two elements of this set, and what you get also belongs in the set. So it's big enough to contain sums of all of its elements. And the second property is this, that it's closed under scalar multiplication. by a complex number. If it is a complex vector space, and that's what we are going to deal in this course. And sometimes people can have a restrictive class of vector spaces with a real vector spaces. So then they are closed only multiplication with a real number. So this means that if you choose some constant C and multiply it with this, so this new vector is also part of this set. And then it has this additive identity in it. So there is this deviation for notation of this additive identity. We actually don't represent additive identity with this symbol. That's so true of physicists. They make conventions, and then at some places they founded those conventions as well. So this is one occasion that we will represent additive identity always with this letter 0. And this has this property that if you add it into any vector from left or right, you get the same vector. Okay. All right. So if your set has these 3 properties, we can call it a vector space. Let me take some examples. So this Euclidean space R2, R3, Rn is a vector space. So in this, let's say R2, the vectors can be represented by a column vector containing 2 elements, or you can represent a tuple like this. And if you similarly in R3, these are 3 the vectors are columns with 3 numbers, and if you want to represent this, might be this vector, this vector, this vector, this, you can. So these are some of the elements of this vector space. Another example could be the C2, C3, and so on. So these are sort of the complex counterpart of these Euclidean spaces. Okay, where these elements A and B could be complex numbers. So for example, in V3, the vector will have some 3 elements where A, B, C, they belong to the set of complex numbers. Here, these elements A, B, they belong to set of real numbers. Okay, sometime, actually many times, we can take a subset of this set, and that still can be a vector space. And then we call this a subspace. W is a set of V if WV both are vector spaces. Let me take another example actually, because this sometimes give a false impression, especially initially in the minds of people, that perhaps all vector spaces have elements that are like this. Let's say a set of, another example, set of all 2 by 2 matrices, and for that matter 3 by 3 matrices and n by n matrices you can have. So this is also a vector space. Even if you restrict them to real numbers, then it's a real vector space. If you allow them to be complex, then it's a complex vector space. And we can show, because the 0, 0, 0, 0 is an identity matrix. You can add it to any matrix and you'll still get the same matrix. And if you, since it has all 2 by 2 matrices, if you multiply a matrix with a complex number, you still get a 2 by 2 matrix. And if you add any 2 by 2 matrices, still get 2 by 2 matrices, under the assumption that you define this operation addition in a specific way. And what's the definition of that operation? It's this, that if you have these two, this is a vector now, this is a vector because they're both elements of this vector space. Then if you define addition in this way, because there's no reason for you to, always define addition in this way. You can come up with another addition operation. Let's say you might be adding this one to this or this to this. And there's a possibility that you can construct an addition operation that this can still be a vector space. But usual vector space of matrices that we will consider will have an addition defined like this. And a multiplication with a scalar defined like this, that you multiply this number with all of these numbers. Perfect. So some quick question. Simple, easy peasy. Good. By the way, तो मैंने तो ये नहीं कहा कि आप जैसे मर्जी करें बन जाएंगे. मैंने कहा you might come up with a way where you define addition in a certain way and still is a vector space. Okay? But in general आप किसी तरह से define कर ले तो जरूरी कि वो हो. You have to make sure that it satisfies, this way. All right. So again, I think it might not be very difficult actually, because जो भी आप तरीका करेंगे 2 by 2 मैट्रिक्स ही निकालेंगे ना, क्या निकालेंगे उसमें से. So it's very easy to construct new vector spaces. Okay, so let's now talk about inner product space. And for that, let's first define what an inner product is. So inner product of two vectors, let's say vector v and vector w. अभी मैं ना इसके लिए ये सिंबल यूज कर रहा हूँ. I know कि आप सब लोग familiar हैं कि you can define vector inner product like this as well, and this is the symbol that we will use later on, but today I'm just going to use this as a symbol for inner product. Okay, so the inner product is a function that takes two vectors into a complex number, and it has three properties for it to be a legitimate inner product. The first is linearity, and that means that the inner product of vector v with the inner product of, let's say, w1 plus w2 is equal to a v plus a comma w1 plus b comma v comma w2. So this means linearity in the this vector, that it distributes over these two things. अगर आप इसको वो usual symbol में लिखेंगे तो this means this. The inner product of v with a w1 plus b w2 is equal to a v w1. Any legitimate inner product will have to satisfy this property of linearity. The second important property is that of skew symmetry, and that is that inner product of v w gives a complex number which is the complex conjugate of inner product of w and v. So there is a conjugate. So if you switch places, the resulting complex number is conjugate of the previous one. Okay, number 3, that if you have inner product of the vector with itself, you will get a real number which is always greater than 0, and it's 0 only if your vector is 0 itself. It's the additive identity itself. So now, what is an inner product space? Inner product space, and you can guess because of this tongue twister, it's easier to call it Hilbert space. So this is a vector space with an inner product defined. Sorry for the spellings. And this initially might seem to be something very strange and extremely different from the classical philosophy. But I didn't explicitly mention there, but that was actually true over there as well. When people had this assumption that we can represent the state of a particle classically with position and velocity, there was another, actually, you have to qualify, and the position and velocity, they lie in a real vector space where you can define the norm of those vectors. And those norms were positive real number. You can define distance in the real space, which gives meaning to if the particle is here and there. Agarche, jo ye wali norm hai, this doesn't have any correspondence with that norm. But physically speaking, but mathematically, there's a great similarity between this first postulate and what was the operating assumption of classical physics. Because people used to work only with real variables. They form real spaces, and the lengths and all these things were positive real numbers. Okay, so जैसे मैंने शुरू में कह दिया कि ये जो postulates हैं, ये ऐसे नहीं हुआ कि एक दिन किसी बंदे ने कहा कि okay, you have these postulates and then you have a new physics. So physics actually worked out later, and then slowly people try to put it into a formalism, and that turned out to be in a simplified way governed by this thing, that if you have a vector that lies in a vector space with the inner product defined certain way, then that correctly describes the physics. Okay. हाँ, तो अभी तो हम चुके 100 साल के बाद पढ़ रहे हैं ना. So we are not starting from Max Planck from 1905 and then spending a lot of time, क्योंकि और खैर अभी भी एजुकेशन ज्यादातर वैसी है. आपने वो पिछले 2-3 साल उन्हीं चक्रों में लगाए हैं. ठीक है. तो क्योंकि अगर आपको पहले दिन ये बताते तो then again this would be have been very hard to answer this question कि where this comes from. Okay. So ज्यादातर दुनिया में अभी भी जो एजुकेशन है वो हिस्टोरिकल, वो क्रोनोलॉजी से ही पढ़ाई जाती है, except for the Feynman's experiment in Caltech. Okay.
ये कंस्ट्रक्ट है कोई रिगरस तरीके से नहीं आया, ये कंस्ट्रक्ट है मैथमेटिकल.
ये कहीं से नहीं, एक्सियम है खुद. अब हाँ, लेकिन ये ऐसे नहीं कर लिए, ऐसे हवा में नहीं किया, क्योंकि it turned out by hit and trial. And for like 10-15 years there was great debate on the meaning of psi, on wave function किसको represent करता है, उसका physical meaning क्या है, कौन सा जो meaning है, it makes much more sense. And then during all these debates these formalism emerged. ठीक है.
Is there any rigorous way to approach these methods?
No, you can't start from paper without any input from experiments and say okay, the and coming from some fundamental arguments, coming up with these axioms. By the way, and people have done a lot of work in this direction. By the way, हम ये जो 4-5 postulates पढ़ेंगे, there's been a lot of effort starting in 1935 by Einstein himself with the EPR paper, that there is some trouble with these, with the quantum physics, might be the hidden variable theory and a lot of these things. And quantum information itself, a lot of people are trying to take a shot from the information route of coming to these postulates. But for this course, since this is sort of an applied course, we are going to start from the postulates themselves. Okay, but it's a worthy, area of pursuit, especially in your free time. Okay. All right, so this is a Hilbert space, and this is where the ray of any physical system lives. And ray means that the vectors are normalized. Okay, let me give you an example again. Let's take the example of this C3. So let's say we have this vector. Okay, let's take it Cn, y1, y2 up to yn. So this is n, this vector with n elements, and then there's another vector. And let's define the inner product, because right now this is just a vector space. And now we are defining an inner product ourselves. Okay, this is not part of the set. Set just has this set Cn has all the column matrices with n elements, complex number. That's it, and it's a vector space. And now let's make it a Hilbert space. And with to do that, I'm defining an inner product between these two vectors in this way. That I say, okay, you take this first element, and then you take its conjugate, then take the first element from here, then take its second element, take its conjugate, take the second element from here, and keep going until the last element. You can write symbolically it like this: sum over I, yi conjugate, zi. If I define an inner product, an inner product is what is, you have to define a function that takes your vectors, two vectors, to a complex number. And this is a complex number. This is still a definition, but now I have to check, does this definition satisfy these three axioms? Because it has to, if I want to make it a Hilbert space. And I'm not going to check it. You can check yourself easily that this definition does satisfy all these three axioms. If you switch places, the conjugate will go to the other place. You have skew symmetry. And since these are simple products, you can check linearity as well. And if both vectors are the same, this is y1 conjugate, this is y1, then this would be y1 mod square, and you are adding just the positive real numbers, you'll get a real number. So this definition satisfies this. I have a Hilbert space. Let me define another inner product for the space of 2 by 2 matrices. Did he?
वो कॉम्प्लेक्स स्पेस में एग्जिस्ट कर रहा होता तो ये तो हिल्बर्ट स्पेस मतलब ये हमने अज्यूम किया ना कि y और z जो वेक्टर्स हैं ये कॉम्प्लेक्स स्पेस से आए हैं मतलब इसलिए लोकल वाली स्पेस से नहीं है
बिल्कुल
ये assumption क्या हमें लिखनी चाहिए
हम ये मैं लिखा हूं मैंने cn से this cn set
यानी इसके अगर एलिमेंट्स हो तो उसमें भी हम एक तरह का और एक और तरह का इनर प्रोडक्ट डिफाइन करेंगे जिससे आंसर c स्पेस भी आए और फिर वो हिल्बर्ट स्पेस बन जाए
बिल्कुल. Okay. All right. So, any questions so far? अच्छा, अब मैं एक और inner product define करने लगा हूँ to convert this set of all 2 by 2 matrices into a Hilbert space. By the way, this course we'll be working with matrices a lot. So that's why, as an example, I'm choosing a little bit atypical Hilbert space for you. एक तो ये कि आपके ज़हन में यही ना हो कि वेक्टर स्पेसेस में सारे वेक्टर जो हैं वो बस कॉलम वेक्टर ही होते हैं. Even the numbers of these types like 1, 2, 3, 4, iota, 0, 1, 2, and so on. So let me call this some set F. So this set can also be converted into Hilbert space with each one of them representing a vector, because they can be used to represent the state of a particle. And there's a special definition for inner product for this, which makes actually this a famous Frobenius Hilbert space. You have Frobenius inner product space. And for this, you define the, let's say this is your vector A, this is your vector B. If you define the inner product of A and B like this, you take trace of matrix product like this. So B Hermitian mean it's the Hermitian conjugate, and A B H mean that this is the matrix product in a usual way. Okay, and this TR mean the trace. Trace में ये है कि हम इसको जो diagonal elements उनको sum करते हैं. Actually, let me check if this is the usual matrix product or a special matrix product. I'll confirm it because I think there is also a vector space which defines the product in this way. That you just multiply corresponding element A1 B1, A2 B2, A3 B3, A4 B4. So this is a matrix product different than the matrix product that we are accustomed to. So I'll confirm you in the next lecture if this is a जो Frobenius inner product space नाम है वो इस वाली का है या usual वाली का है. But the point is that this set of 2 by 2 matrices can also be converted into a vector space by defining an inner product that satisfies these as axioms. जी मैं इसलिए मैंने ना वो लिखा नहीं हुआ कि ये वाला है या यूजुअल वाले का नाम फ्रॉबिलस है. प्रोडक्ट का नाम या वेक्टर स्पेस का नाम? Okay. All right. So next, let's define another thing. It's the normalized vectors, or you can call them unit vectors. Or there's another name for them. You can call them ray. So a normalized vector is just a vector that has the norm as 1. And what is norm? Norm is defined as the square root of the inner product of the vector with itself. So let me use the proper symbols for this. So this is how we are going to define this quantity, what we usually call magnitude. So magnitude जो है उसके लिए symbol हम ये double line वाली use करेंगे. So if a vector has a magnitude 1, it's called a ray or unit vector. And you can easily convert any vector into normalized vector by dividing the vector with its norm. Okay, so this will always have magnitude 1. Another definition, orthogonality. If the inner product of 2 vectors is 0, we say the vectors are orthogonal. And if they are normalized as well, then we say the vectors are orthonormal. All right. Let's now discuss the idea of spanning set. So a spanning set is a set of vectors that spans the vector space. That with just those vectors, you can write any other vector of the vector space by a linear combination. For example, for the set F of 2 by 2 matrices, I can define a spanning set like this. Let's say 1 0 0 1 1 0 0 1 1 1 0 1 1 1 1, because I can express any element of this set as a superposition of this. You can check it. And actually, for spanning set, I can even include this as well. Like this. So this can also be a spanning set. The basis set is a special spanning set such that all vectors in this set are linearly independent. So in this, all are not linearly independent. I can easily write this element in terms of this. By multiplying it with 2, I can get that one. The last one I can get by subtracting this from this and then multiplying with 3. But a basis set has only those elements which are linearly independent, which means that if you have, I sum over I equals 0, this means that all the coefficients have to be 0. जी Heather? जो स्पैनिंग सेट है उस पर कोई रिस्ट्रिक्शन नहीं है, बेसिस पे है. हाँ, तो what basis? Then we have this definition that number of element in basis is equal to dimension of the vector space. But spanning set पे वो restriction नहीं. And as you can see that there can be many more bases of the same vector space. For example, अगर ये 2 by 2 matrices की बात करें ना, तो एक basis हो सकती है 1 0 0 0 1 1 1 0 1 1 0 0 1 1 1 1. So this is one basis. There can be another basis 1 0 0 1 1 minus 1 0 0 iota, I think minus iota 0, then 1 1 0. So this can also be a basis, and there can be many more. You can have one here, one here, one here, one here, all other zeros, and so on. And ये भी basis है क्योंकि इसके चारों linear independent, इसके भी चारों linearly independent. Okay, but there is one important thing that we have to do many times in quantum physics, and that's a procedure that I'm going to describe now. It's called, it's a way that अगर आपके पास कोई vector space है and you have its basis, और basis जो है वो of course उसके सारे element linear independent है, but you want an orthonormal basis. Okay, you have a basis of linearly independent vectors, but you want to convert it into another basis which is orthonormal. उसकी वजह ये है कि I'm sure that by now you know that life is much easier when you work with orthonormal vectors. Lot of inner products goes to 0, and even when there's an inner product with a vector itself, it's 1, right? But if you have linear independent, then you might have to work out inner product with many other vectors. But not only that, there's another big trouble, which is actually even more important when it comes to quantum physics than just this mathematics, because you can do mathematics in computer. That's not a big issue. The issue is trying to make sense of equations. When you have a set of vectors, let's say an equation where there are a lot of different vectors are adding up with some coefficients, and they're not orthogonal from each other, you can't really talk much about them, what they represent, because one might have a component along the other and so on. But if you have an equation that is superposition of sort of orthogonal or orthonormal vectors, You can try to make sense, okay, this vector has a component along this direction or this direction, and those different directions might represent some physical things. So that's why it's very important, and we will be doing it many times, that we will have to convert a basis, which is a set of just a usual basis like linearly independent vectors, but not orthogonal, into a set of orthonormal vectors. The good news is that it's extremely easy. Okay, at least intuitively. And since people are afraid of this mathematically, what I'm going to do first is just going to describe you the procedure geometrically. And hopefully you can guess the mathematical framework yourself right away. Or at least if I write it in front of you, you can just say, okay, yeah, that makes sense. So for that, let me start with a vector, a two-dimensional real vector space, because it's easier to draw on the board. So I know many of you are familiar with this basis for this vector space. A unit vector along x-axis, a unit vector along y-axis, right? But that's not the only choice. I can also have a basis like this, that I have one vector like this, another vector like this. Let me call this v1, and let me call this v2. This is an equally good basis. And I can describe any vector in terms of these two vectors as well. And let me take an example. Suppose you have a vector like this. I can compute its projection along this vector, and suppose this is some number a1, and I can compute its projection onto this vector, and let's say this is some a2, and I can say that my red vector R is a1 v1 plus a2 v2, right? And if I was using this usual basis, I could have done the same, that I would say, okay, let me take a projection over here and a projection over here. So I could also have written this R like, let's say this component now, we can call it some AX, and this component some AY. So I can represent it like this. And when we look at this, we can say, okay, AY is the magnitude of the vector along this, and AX is the magnitude of the vector along this. And when we look at this, we can say that, okay, this is a vector whose magnitude or direction or projection along V1 is this, and along V2 is this. And let's now try to construct an orthonormal basis starting from the this linearly independent basis. Okay, so let me do it here. So this is the starting basis. So the method discovered by Graham and Schmidt is this, that you choose one of the basis vector arbitrarily. Any vector you want, you can choose. Of course, then you will get a different orthonormal basis, but you will end up having an orthonormal basis no matter what. So for the sake of argument, let me choose this to be my first vector. So what I do that, okay, this is some vector v1 and this is some vector v2. So I choose my first unit vector as v1 divided by v1 now, because these v1 v2 doesn't even have to be normalized. We can still work out. So I choose one of the basis vector and normalize it. And my new basis, and I'll have this vector over here. So this is what I have got. Now I need another one because the number of vectors in each basis has to be the same, equal to the dimension. So for the second one, when I go to here, I see that when I look at this vector, it has some projection along this, and it has some part which is, perpendicular to this. So what I do that if I want to find this vector, which is orthogonal to the first one, all I have to do is कि ये जो वेक्टर v2 है इसका पहले मैं प्रोजेक्शन फाइंड कर लूं 1 के अलॉन्ग, v1 के अलॉन्ग नहीं करना, ठीक है, क्योंकि इसके और इसके मीनिंग में फर्क है। ये हमें ये बताता है प्रोजेक्शन ऑफ r अलॉन्ग x, ये जो है ये हमें ये नहीं बताता कि r का v1 के अलॉन्ग कितना प्रोजेक्शन है, क्योंकि अगर लेट्स से इस वेक्टर की अपनी लेंथ 1 मीटर है और ये जो v1 है ये 10 मीटर है, तो आप पहले देख सकते हैं कि इसका प्रोजेक्शन इसके अलॉन्ग जो है ना वो काफी ज्यादा होगा, 4-5 मीटर के करीब होगा, ऐसे ही है ना, because you have to find its inner product with that one. Okay, so this is sort of a scaled version with the magnitude of this one. So that's why I'm finding its projection along 1 and not along v1. तो इसका प्रोजेक्शन इसके अलॉन्ग फाइंड करके देन जो ये वेक्टर है इसमें से मैं इस प्रोजेक्शन को माइनस कर देता हूँ जो ये है। सो चूंकि जो ये वेक्टर है आई कैन राइट दिस एज सम ऑफ दिस वेक्टर एंड सम ऑफ दिस वेक्टर। तो अगर इसके अंदर से मैं इस वेक्टर को माइनस कर दूं आई गेट दिस वेक्टर। सो द सेकंड वेक्टर इज v2 minus the projection of v2 along my first vector divided by its magnitude. So this is my new basis. और इसको मैं अगर ड्रॉ करूं तो ये हो जाएगा, एक ये बेसिस वेक्टर आ गया यूनिट वेक्टर, एक ये आ गया। इस बात को समझ गए? तो दूसरा वेक्टर जो है उससे मैंने जो एक वेक्टर भी ले चुका हूं उसके अलॉन्ग उसका प्रोजेक्शन फाइंड किया, उसको इसमें से माइनस कर लिया ताकि इसके अंदर से वो कंपोनेंट निकल जाए जो इसके अलॉन्ग था, एंड देन आई नॉर्मलाइज इट। एंड यू कैन आल्सो सी दैट इफ आई हैड स्टार्टेड विद दिस वेक्टर आई वुड स्टिल एंड अप विद एन ऑर्थोनॉर्मल बेसिस, लेकिन अब मेरी बेसिस क्या होगी, पहला वेक्टर मेरा ये होगा और दूसरा वेक्टर जो है पहले इसका मैं प्रोजेक्शन फाइंड करूंगा इसके अलॉन्ग और इसमें से इसको माइनस करूंगा तो आई विल गेट दिस वेक्टर। सुभान ओके जी हैदर, थैंक यू, गुड पॉइंट। So I will write one here, one here. Good point. ठीक है, क्योंकि ये तो कंपोनेंट है ना, तो जब इस कंपोनेंट को मैं इस वेक्टर के साथ लिख लूंगा, सो दिस इज द सॉर्ट ऑफ द वेक्टर अलोंग दिस डायरेक्शन। सो इसमें से इसको माइनस कर लिए, और अगर आप इससे स्टार्ट करते हैं यू विल स्टिल एंड अप विद एन ऑर्थोनॉर्मल बेसिस बट अ डिफरेंट वन। मामा समझ आ गई, पता चल गया? सो और अगर आपके पास तीन वेक्टर्स होते हैं, लेट्स से मैं 3 डायमेंशनल स्पेस में हूं और एक ये भी है, तो थर्ड वेक्टर जो है वो क्या होगा, वो होगा कि v3 में से, अब इसको जो है मैं वो कह देता हूं वेक्टर नंबर 2। तो v3 में से पहले मैं v3 का प्रोजेक्शन फाइंड करूंगा जो इस वेक्टर के अलॉन्ग है। तो v3 का प्रोजेक्शन 1 के अलॉन्ग, 1 साथ लगाया यूनिट वेक्टर, तो ये वेक्टर बन गया। फिर इसमें से मैंने, हो सकता है इसका प्रोजेक्शन इस वेक्टर के अलॉन्ग भी कुछ हो, तो फिर इसका प्रोजेक्शन जो है वो v3 का 2 में से भी माइनस करके 2 में, और इसको फिर इसकी जो मैग्नीट्यूड है उससे डिवाइड कर देंगे। सो दिस वुड बी माय थर्ड ऑर्थोनॉर्मल बेसिस वेक्टर, and this is a way we can continue and construct a new orthonormal basis. Okay, so let me put the general rule over here, and this procedure is called Gram-Schmidt procedure of constructing an orthonormal basis from a linearly independent basis. And this is at the heart of a lot of things that we will do later on. And in general, you can write the So the first vector in the basis is always any vector that you choose, just normalize it, and then after that the k plus 1 unit vector is from the k plus first vector, you subtract the projections of your k plus first vector on the previous unit vectors, and then put vi here and divide it with and normalize it. So all of this over here and its magnitude. So this is the Gram-Schmidt procedure. So basically we will be working with the density matrix formalism, where the space would be the Hilbert space of matrices, and then rays would be matrices. And many times when we study the entanglement and how to, quantify it or get information out of it, we might be needing these types of procedures.
पहले तो कभी मैंने मतलब जितनी बार मैं ये पहले तो कभी इनको जब आइगनवेक्टर से निकालने तो ऑर्थोगोनल आना
ये आप छोटी क्लासेस की बात कर रहे हैं ना, उसमें जनरली एग्जांपल्स ही ऑर्थोनॉर्मल की दी जाती है, बट देयर इज नो हार्म इन हैविंग एंड वर्किंग विद नॉन ऑर्थोगोनल वेक्टर्स. नहीं, पहली बात ये है कि डिजेनरेसी से इसके ताल्लुक नहीं है. जब लीनियर इंडिपेंडेंट है तो वो नॉन डिजेनरेट स्टेट्स तो ऑलरेडी है. ठीक है. और एज फार एज मैथमेटिक्स इज कंसर्न, देयर इज एब्सोल्युटली नो बार. सिर्फ इंटरप्रिटेशन में मसला फिर आता है, क्योंकि जैसे हमने लिखा था, जब आपके पास लीनियर इंडिपेंडेंट वेक्टर है, किसी की लेंथ कुछ और है, किसी के, तो जब आपको कंपोनेंट मिलते हैं ना उनके अलॉन्ग, यू कैन से मच. जिस तरह अगर आपने ऑर्थोनॉर्मल बेसिस में ब्रेक किया हुआ वेक्टर को, तो आप आराम से कह सकते हैं यार इसके अलॉन्ग इतना कंपोनेंट, इसके अलॉन्ग इतना कंपोनेंट. यू कैन कंस्ट्रक्ट अ मेंटल पिक्चर. तो उसके लिए आपको मेंटल पिक्चर बनाने के लिए बन जाती है, बट इट्स अ कन्वोल्यूटेड वे कि आपको वो जो बेसिस वेक्टर है वो भी हर दफा साथ याद करने होंगे कि v1 मेरा जो है वो 10 मीटर है, x के लॉन्ग मेरा जो v2 जो दूसरा बेसिस वेक्टर है वो 45 एंगल पे है, और उसकी लेंथ जो है वो 0.1 मीटर है. सो जब आपको मैं दोनों के लॉन्ग कंपोनेंट दूंगा, तो हाउ डू यू ट्राई टू अंडरस्टैंड कि आपका असल वेक्टर है कहाँ पे. सो यू विल हैव टू पुट दोज नंबर देयर, गेट द वेक्टर, एवरीथिंग आउट, ड्रॉ. फिर आपके समय बनेगा इतना यार यूं लाई करता है. तो ऑर्थोनॉर्मल का ये फायदा है कि जो ह्यूमंस हैं कम से कम, और perhaps दूसरे एनिमल्स भी, दे आर ट्यून्ड टू वर्किंग with these types of things. I don't know, maybe because of gravity affecting our evolution, that we're like upstanding all the time, and we know that when we move on a plane area, we don't have to spend too much force, and when we have to go up, it's really extremely difficult, so on. But there is something for psychologists to work on this, that why it's natural for us to work with orthonormal basis besides the very elegant mathematics. तो या फिर ये है कि बनाने वाले ने इतनी खूबसूरती से चीजें बनाई है कि somehow you wonder कि why things fall so much perfectly in place, कि ना सिर्फ मैथमेटिक्स आसान है बल्कि उनको विजुलाइज करना भी आसान है. जी जी.
अब ना एक चीज इस तरह लगती है कि इनर प्रोडक्ट जो है वो कंस्ट्रक्ट है, इससे हम ये नजर आते हैं कि जो उसका लेंथ 1 होनी चाहिए या उनका एंगल परपेंडिकुलर होनी चाहिए, वो हम वेक्टर स्पेसिस के साथ अपनी मर्जी से भी डिफाइन कर लेते हैं. तो वो भी एक कोई जिस तरह हमने वो ट्रेस ऑफ दिस मैट्रिक्स इनटू दिस मैट्रिक्स लिखा हुआ था, तो एक सिर्फ एक कंस्ट्रक्ट है जो आपने बनाया, इनर प्रोडक्ट किसी भी तरह डिफाइन कर सकते थे. तो उसमें फिर आपकी ऑर्थोनॉर्मलिटी और ऑर्थोगोनैलिटी की डेफिनेशन चेंज हो जाएंगी. तो वो यू कैन मतलब कम अप विद के नहीं, ये एक
मैं समझ गया बात. असल में हम चूंकि रिवर्स में पढ़ रहे हैं, दिस इज नॉट द वे इट वाज डेवलप्ड. लोग यूनिट वेक्टर के साथ पहले काम करते थे, आज से 500-600 साल पहले पीपल हैड paper and pens and vectors and these things, and these axiomatic approach and these came later, inspired by that. So हम अक्सर जो advanced courses especially we try to reverse that approach. उसकी वजह ये है कि especially physics में we try to think of everything happening according to some few number of principles or rules. क्योंकि जब हम समझ लेते हैं चीजों को कि अच्छा यार अगर ये जो 4-5 एक्सियम्स हैं अगर ये सेटिस्फाई करें तो आई कैन ऑलमोस्ट एक्सप्लेन एवरीथिंग इन द वर्ल्ड. तो बात असल में उसके बाद आपको ये सारी तैयारी की जा रही है, उसके बाद चीज की जा रही है कि जब आप 60-70 साल के बूढ़े हो जाएंगे देन यू स्टार्ट थिंकिंग अबाउट दीज एक्सियम्स कि इनमें ऐसा क्या है कि यू आर गेटिंग एवरीथिंग राइट. तो अभी तो ये लर्निंग फेज है और उसमें वो अब हम इन्वर्टेड अप्रोच की तरफ आ रहे हैं. ज़ाहिर मैट्रिक में जब आप लोग वेक्टर सीख रहे थे और कंपोनेंट उस वक्त तो एक्सियम्स की बात नहीं की. सो इट्स कमिंग फ्रॉम देयर. हमें ऑलरेडी पता है कि इस तरह के साथ लाइफ आसान है और लास्ट सेंचुरी के शुरू में आस्ता आस्ता पता चल गया कि अगर हम ये मैथमेटिक्स यूज करें तो वी कैन राइट थियरीज इन अ वे दैट मेक सेंस फिजिकली. सो इन्वेंट उल्टी हुई थी, पढ़ाई जो है वो उल्टी जा रही है. और प्लस ये फिजिसिस्ट और मैथमेटिशियंस का ये पर्टिकुलर वे है. ज्यादातर जो लोग हैं दे लाइक डिडक्टिव लॉजिक दैट ओके यू टेल मी व्हाट आर द मिनिमम नंबर ऑफ लॉज दैट आर देयर टू मेक सेंस ऑफ द होल यूनिवर्स. तो ताकि आप उनके बारे में सोच सकें. एट द एंड तो शायद ह्यूमैनिटी के शुरू से मकसद यही है ना कि ट्राई टू सी व्हाई वी आर हियर, ट्राई टू फाइंड सम ऑफ or this is sort of a way that will perhaps take us there. I don't know. Maybe there's something else later on, but that's what seems right now. आप अली साहब कुछ कह रहे हैं? बिल्कुल. So that 90 angle where it started. So that was the initial intuition. और उसी के बेस पे जैसे जो ये चीजें बिल्ड है. But of course when we have complex number then you can't even imagine the direction and those things.
नहीं मतलब वो तो हमारी विजुअलाइजेशन की लिमिट है ना, लेकिन असल में ऑर्थोगोनैलिटी तो हमें डिफाइन यानी डॉट प्रोडक्ट से भी इनर प्रोडक्ट आ रहा है तो डिफाइन होना ही इस तरह चाहिए कि कुछ ना कुछ तो ऑर्थोगोनल है तो वो इनर प्रोडक्ट 0 आ रहा है. तो फिर
नहीं, ऑर्थोगोनल इनर प्रोडक्ट 0 एक ही बात है. उसमें कोई ये तो नहीं कि मेरा नाम फरियाद है तो मेरा नाम फरियाद है. अब ये तो दो नाम है ना एक चीज के. तो जो ज्योमेट्री और मैथ का कनेक्शन आप सिर्फ रियल स्पेस में कर सकते हैं, वो भी अप टू 3D. आफ्टर दैट इट्स जस्ट टॉर्चरिंग आवर ब्रेन्स टू इमेजिन दीज थिंग्स. Okay, so I actually had a quiz for you today, लेकिन हम नहीं करेंगे, आप घर में खुद कर लीजिएगा. I wanted to ask you to prove that these are really orthogonal to each other. कि अगर आप एक VK+1 लेते हैं या VK लेते हैं और इसका इनर प्रोडक्ट बाकी तमाम VKs के साथ लें जिनका सबस्क्रिप्ट इससे डिफरेंट है, you will get the answer 0. But that's an exercise you can do yourself. Okay, so perfect. We will continue the discussion and postulate into the next week. अच्छा, मैंने एक चीज आप लोगों से पूछनी है कि हम ट्यूटोरियल्स किस वक्त